In this video, we're going to talk about electrolytic cells, and we'll look at an example of an electrolytic cell and walk through how it operates. So this is an electrolytic cell, and we're going to start by walking through some differences between an electrolytic cell and a voltaic cell, which we've been studying to date. So the first thing that you may notice is that there is no salt bridge or porous cup between the two compartments. That's because in an electrolytic cell, there is no need to separate the two half reactions because the reactions are non-spontaneous. So in this cell, we'll see at the top that we have a battery. That's because in an electrolytic cell, we are taking electrical energy and we're converting it to chemical energy, the opposite of a voltaic cell. So those are the main differences in an electrolytic versus a voltaic cell. We're going to take this simple cell that's drawn and we're going to walk through what's happening in it. So first things first, we see that we have our battery, and our battery is connected to our anode and to our cathode. And we see that the battery itself has signs, negative and positive. The negative terminal of the battery is the anode of the battery. That means that electrons will flow out of the negative terminal of the battery. Because electrons are flowing into our electrode, the cathode of our electrolytic cell is attached to the anode of our battery. In this cell, both our cathode and our anode are inert carbon electrodes. Electrons enter our cathode, and the same as we would have in a voltaic cell, the cathode is going to be the site of reduction. And our strongest oxidizing agent will be the thing that is reduced, same as in a voltaic cell. Within our solution, cations will flow towards the cathode, just as in a voltaic cell. Anions will flow towards the anode, which is the site of oxidation of the strongest reducing agent. In our anode, as oxidation occurs, electrons will leave the solid anode and move towards the battery, entering the cathode or positive terminal of the battery. The charge on the electrodes in an electrolytic cell is actually different than that in a voltaic cell. In an electrolytic cell, our cathode is negatively charged because we're adding excess electrons to it intentionally to force a reaction. So there's a buildup of negative charge. The anode is positively charged because our battery is pulling excess electrons from it without a spontaneous reaction, causing a lack of electrons or a buildup of positive charge. So in a battery, our cathode is positive. In an electrolytic cell, our anode is positive. In a battery, our anode is negative. In an electrolytic cell, our cathode is negative. But the rest of the operation of the cell is the same. So cations move in the same direction, anions move in the same direction, electrons move in the same direction. We're now going to use the 5-step method to walk through what will happen in this cell. So we're going to start by listing our species present. In this cell, we have copper 2+ in our solution. We have bromide ions in our solution from the copper bromide, and we have water. I'm not going to list the inert electrodes because they are inert. So using the table you have on page 7, we can identify our strongest oxidizing agent and our strongest reducing agent. Copper is our strongest oxidizing agent. Bromide is our strongest reducing agent. So at our cathode, our strongest reducing agent, which is copper 2+, will be reduced to copper solid. In terms of observations that we might see, or that we will see in our cell, we're going to see plating of copper, so kind of an orangey brown metal, on our cathode. This reaction also reduces the concentration of copper 2+ ions in our solution, and copper 2+ ions are blue in color. So as this reaction proceeds, we'll see the color of our solution start to lighten. At our anode, we're going to have oxidation of our strongest reducing agent, which is bromide. So bromide ions will form liquid bromine by losing electrons. Now liquid bromine is a brown-orange liquid that is denser than water. And so you're going to start to see this liquid form and settle on the bottom of our solution. Water and liquid bromine are not miscible because bromine is nonpolar. So we'll see this liquid forming on the bottom, kind of like an oil and water situation. To calculate E cell, we're going to use the same formula we've been using all along, which is the E0 value of our SOA minus the E0 value of our SRA. So our SOA is copper. It has an E0 value of 0.34 volts. Our SOA is bromide, and it has an E0 value of positive 1.07 volts. That gives us an E cell value of negative 0.73 volts. The negative cell potential indicates that the reaction is non-spontaneous, and all electrolytic cells will have an E cell value that is negative. We can use this value to understand the minimum potential needed to operate the cell, and that is going to be the positive or 0.73 volts. So our battery must be at least 0.73 volts for this cell to operate.